Hello and welcome to another session, and today we're gonna have a look at some classical word2vec model. And as you can see, we are already here within Google Colab. We are already at close to 8 gigabytes of RAM. We have, of course, here a limitation. Our GPU that we're running today is a Tesla T4. And I already have 4 epochs done. And the accuracy is looking not too bad, but let's start at the beginning. What have I done? Where are we? This is a very classical model that I designed, a typical word2vec model. My word target, my word context. I have my labels. I've chosen 20 epochs, my batch size. I've chosen the vocabulary size, since I find if you load the whole vocabulary within the batch size, you get better results, in my opinion. And since I do not have to do any prediction with my word2vec model, my validation split can be, of course, very, very small, since what I'm interested in is the weights in the hidden layer of my shallow neural network. Those weights for each of my words in my vocabulary. This is exactly the embedding that I'm looking for, a word embedding I'm looking for here. And if you ask, okay, what is the vocabulary size that you mentioned? My vocabulary size here is, my vocabulary size is 50,391 words. So for all of those words, I calculate in a 128-dimensional hidden layer. This is the dimensionality with a negative sampling rate of 0.7 and a window size from 5. This is given my RAM limitation of only 12 gigabytes of RAM on an NVIDIA GPU graphic card. If you have a better GPU available, please increase your window size. Maybe also increase from 128 to 256 dimensional embedding. And if you can afford negative sampling rate, set it to 1. That's the same amount of the negative samples as the positive samples. And this is it. I have all my sentences from all the 34,000 R&D research projects by the European Union, signed and executed within the last 5 years, and signed that should be executed within the next 5 years, so where we have the financial allocation already today. And from those projects, I have here all the sentences, and the sentences are exactly here. The sentences I load from a word2vec model. So now you're up to speed with me. From a layer type, you see that I have the most simple layer structure that we have. The target input and the context input layer, my embedding. I do some reshape. I have, of course, the dot product. I want to see how close they are. I do some reshape, and this is it. The number of total parameters that I can train is 6.45 million free parameters, and this is more or less it from the model size. So I'm now in epoch number 7. The accuracy is 88%. This looks good. If you want to increase it after you have run your 20 epochs, it is very easy. I found this way, since the model is still the model within the cache. So I just start again the same model fit, label epochs, then I've chosen 10. Batch size is, of course, again vocabulary size, and the validation split is identical to the other run. And then you can save it. And as you can see here from another project that I've done, I reached after 20 epochs an accuracy of 92% here, 92.3%, and I ended after another 10 epochs 92.7%. So we're here already plateauing out, but since this is now only for demonstration purposes, this should not be of our concern. So what we're waiting now is that the 20 epochs finish, and then I'm going to show you how I proceed with this problem. See you in a second. And after 40 minutes, we are back, and we are epoch number 20 of 20. Our accuracy is 92.3%. Loss is about 0.2. This is fine for demonstration purposes. Remember, my validation accuracy It's just minuscule, so whatever there is, it is above 80%, which is fine. So this means we have our weights from the hidden layer. This is great. So now what we're gonna do? We are gonna deduct the weights. So, and we save it. We save it to 2 files. And we have now a file with the name meta and a file with the name vectors, a TSV file, where we have our 50,391 words and a 128-dimensional embedding of each and every word in our vocabulary. Congratulations, we achieved it. Now, to calculate now something like a semantic vicinity, we of course have to define a cosine similarity. You can play around. I found that the cosine similarity here, the dot product with the norm, is quite nice. It is quite fast. And to check it out, we have a nice convergent rate, but to make sure that it makes sense, because sometimes it converges, but it makes no sense at all, believe me. I take a search word like urban, and I want to have a look at all the semantic words close to urban. I want to see what the system comes up with from the embedding side. So I say, hey, calculate now around urban, the epsilon vicinity, the epsilon environment, around the coordinates, the 128-dimensional coordinates of the point cloud for the word, for the point urban, and give me back the results. So this takes some time, since it has to run through all of the 50,000 words and checks. Come on! Yes, you can do it! You can do it, baby! Come on! The target word here is this. This is the urban. And my words are urban, cities, city, rural, mobility, area. So urban and cities, that's similar. Semantic similarity, yes, very nice. Citizen, urban, scenarios, pollution, land transportation, waste, trends, authorities. Everything connects with urban, so seems that our calculation also makes sense. Congratulations. Now the next step is to save it, because maybe we want to come back and have some other calculations. So I just save my tensor to a CSV file. And of course, to have it permanently, I just copy it over to my Google Drive. And this is it. So the next time I come back here, I just need to reload it here. So what is my DF3? I have here my words. And for each and every word, as you can see here, I have a 128-dimensional coordinate system, an artificial embedding in a no, it is not even a topological space, but who cares? And we can now work with this. Now, you might say, hey, okay, now we have a 28-dimensional space. Can we now simply apply some dimension reduction for simplicity of our calculation? I would say no, because when I try to reduce here the complexity to a 12-dimensional space, I lost a lot of the semantic vicinity that is hidden here in the coordinate system. So I would recommend go with your full coordinate system of 128 dimensions or 256 dimensional spaces. Yes, of course, it's going to take a little bit more compute time. And as you can see here with the RAM, we are still orange, so no problem at all, not even red. Yes, it takes a little bit time, but believe me, you get a much better accuracy if you perform it in this way. So, and what I want to show you now, koalas, we could also opt for koalas, but we are here in a panda data frame with a low-dimensional thing, so no problem at all. And what I want to show you now is if you have multiple words, and this is exactly what I'm interested in. So let's say here I have the word city, I have the word urban. I'm interested, how is water, the epsilon vicinity of water in the semantic context, given only by the sentences, only by the content of the 34,000 R&D project. How is water interlinked to city and urban? How is water interlinked to social, pollution, air, transport, mobility, networks, health, whatever you define here. You can do it whatever you want. If you see here from my last query, it was about particle physics, high energy physics for CERN, quantum, quark, Higgs, QCD, gravitational gluon topology, symplectics. Whatever words come in your mind, if they're part of the vocabulary, it is very easy. You take them, you calculate here the numpy cosine, the similarity, you put it in a data frame, and you run through all of the data, all of your vocabulary, you calculate all the cosine similarities, and you come up with the result. Now, as you can see here, we are real time. It takes, I don't know, 20 seconds per word. So if you have 10 words, it's gonna take 200 seconds, but no problem at all. Let's have a peek preview. What we're gonna do. Of course, I wanna have a visualization. And I go with Plotly. I have Matplot, and then I have just the renders. I use an iframe here in Colab. And important is to set the node degree. And then you have here two options. If you want to see all edges visible, you set simply the node degree to 0. Or if you want to have only the edges that are multiple connected to multiple words, you set the node degree to 1. And the other parameter you can play around a little bit is the cutoff parameter. As you already seen, let's go back here. Yeah, it doesn't matter at all. Complexity here. We have a cosine of 1. This is, of course, the word, our first word. And then we calculate here the semantic closeness of other words. And you see here the cosine similarity. It is decreasing. So sometime if you have, I don't know, row number 50, then you have 0.3. And you have somehow have a cutoff because it doesn't make sense. Sometimes it makes sense to use the 5 words closest to your target word, or maybe 10 words in the semantic similarity, but not so much else. So there is no degree. Where are we? There's this cutoff, and I would say it is between 0.5 to 0.3. 0.33, 0.43, I don't know. We have a look at this. You can play around with this. You have, let's calculate the visualization. I'll show you how sensitive the cutoff is. But of course, at first we have to calculate. Where is it? Here. Our embedding on our cosine similarity. 4 specific embeddings we have chosen. And what other words are close to our embedding of the word city, of the word urban, of water, social, pollution, air. Air, so we have 1, 2, 3, 4 left. Transport, so we have 3 left. So given the threshold limit, and I'm interested only in a multi-referenced word, in a multi-reference epsilon environment, I've chosen my node degree manually to 1. If you want to understand the whole complexity and you say, okay, the data should be distributed on a topological manifold and smooth and whatsoever, you can go with 0, you can have a look at this. But let's, for simplicity, for demonstration purposes, let's have a look at 1. And let's see how you can play around with the fine-tuning parameters. Come on, mobility. What are we looking for? Networks and health. Well, in a city, networks are essential. Health could regard in reference to humans, healthy ICT networks, healthy energy, transportation networks, logistic networks. It's up and running, so come on, another 20 seconds. Our RAM looks good. We're at 8.1 gigabyte. If you have the chance, I really would recommend, if you want to invest some money, go here and buy some bigger RAM. It really pays off. So, and here we are. So let's run through the initialization of Plotly in 3 dimension. Yes, I know this is not loaded. Then we have here the node degree. And we can have now a look. at the node. So now if I have these parameters here with, where are we, 0, 3, 3, and 1, I have 194 nodes. That's a little bit too much. For demonstration purposes, I just go with 143. Oops, still, okay. So let's choose this visualization just for a short view in 2-dimension, and you get a good idea what I'm talking of. So here we have our target words: health, social networks, urban, city, mobility, transport, water pollution, air, city, and urban, of course, being the most significant, or I'm the most interested in. And you can see we have here no node in our graph, in our network, where we have just a singular link to something, to another node. It is always that it has a reference from at least 2 nodes, and this is what I'm interested in. And you can see here, city is surrounded by transport, mobility, urban networks. That's of course clear. You have here more or less a little cluster: pollution, water, air, health, social networks, transport, and mobility also are close by. This is exactly what we would expect, that the word semantic closeness of the words transport and mobility are closer than to any other words. So this looks good. And in blue, light blue, we have all the other words that our shallow neural network identified to be in a close semantic vicinity, given our 34,000 research projects. Of course, you could now say, hey, I want to have only the projects that will start in 2021, the second half, and will go to 2024 or 2025. Or you have a look at, I don't know, 2020 and the year 2021, or the projects that will end in 21. So you can play around, you get a lot of these insights. If you want to construct it, let's see if I have this here. No, I have not loaded my data. I have written a short Python program for some graph visualization given the Force Atlas 2 algorithm. I have some scaling factor. Yes, I can load it. Wait a second. I will be back in a second. Hold on. And we are back, and I have downloaded here my Python program now to Colab. I uploaded it to Colab, and we're running through it. I have a number of iterations, 1,500. Oh, well, this is gonna take some time. RAM is still okay, no problem at all with RAM. I have to manually check a threshold low. So you can see here the threshold low. I make it very simple. It's 0. The threshold 1 is my high threshold. I calculate all the wedges and all the number of nodes displayed and what the hell ever. So let's see how it looks like. Oops. Unable to connect. Of course, yeah, this is not possible. I know. So hold on a second here. Can I do this and show you? Yes, graph 3D, graph 3D. Come on. Here we go. Yes, I make a download and I show you in my open with Firefox. So you can see it here now. And it's the same representation, simply in a 3-dimensional space, what we have already seen in a 2-dimensional space. And since I'm running here now on my local machine, it's going to take a little bit of time to do the calculation. So come on. Let's celebrate. Okay, I would say I come back. It's going to take some seconds to wait. I come back. And here we are now. We have now Network X graph in 3D. And this is exactly what we have been looking for. Here again, we have city. We have our urban cluster. And then mobility, transport, pollution, air. Again, what we have seen in 2D, but now we have the beautiful option to visualize it in 3D. Now you could cut back on the number of edges, that it becomes a little bit more clearer what we are looking at, but I think you get the idea. You can have now visually all the interlinks between the topics that are of interest for you, for example, mobility, urban and city. How does it respond to? You don't have to put in 8 words or 10 words. You can have only 2 words or only 3 words. Then yes, maybe it's a little bit clearer, but it is not normally not that a complex system has quite a high number of dominating parameters within the complexity. So you have to choose your words that you're interested quite sensitively. But water, chemical, membranes, hydrogen, gas, wastewater, heat, remediation, air, fuel, temperature. This looks good, so you get a quite nice idea what's going on, city urban context of mobility, transport, and so on. And it will augment your knowledge that you already have. Of course, you can further increase it, and this I will show you in the next video. For today, I say thank you and see you next time.